and welcome to the Terminology Leading Practices stream of SNOMED CT Expo 2022. My name is Terence Sherd. I'm the Technical Operations Manager at SNOMED International, and I'm going to be moderating today's session. All questions will be answered at the conclusion of the presentation. Online attendees, please use the Q&A box at the bottom of the screen to type your questions to the presenter. On-site attendees will be having a microphone that will pass around for your questions. I'm now pleased to introduce Eunsuk Chang from the Republic of Korea Air Force, who will be presenting a vector-based semantic relatedness measures using multiple relations within SNOMED CT and UMLS. Eunsuk, thank you very much. Please proceed.
Thank you for introducing me. My name is Eunsuk Chang, and I'm from the South Korean Air Force. Today, I'd like to talk about something theoretical to propose a new vector-based measure, relating measures that tracks word vectors from the intrinsic structure of SNOMED CT and the UMLS, and does not require like a logical prep to learn context around the words. So in the field of biomedicine and translation and research, textual resources are expanded, but many remained unprocessed. To address this, semantic technologies gain attention from researchers for their ability to appropriately interpret information from heterogeneous resources. And measuring semantic relatedness or similarity between biomedical terms contributes to the integration and distribution of knowledge acquired from different sources, and the NLP technologies such as word sensitive mediation, which relies on the measurement of semantic similarity. So before we move on, we need to address the difference between similarity and relatedness. Similarity refers to the likeliness of meaning, whereas relatedness refers to the degree to which two words are associated with each other. So for example, car and engine are not similar because car is not engine or vice versa, but car and engine are related because an engine is a part of a car. So we can measure similarity using ontology, and the basic idea is that similar words are located close to each other in ontology. So the semantic similarity can be measured as the degree of the proximity on ontology. So for example, when we measure similarity between terms between strong and info on SNOMED CT, city's easy hierarchy, you can notice that the concepts are geographically further than expected because the concept stands at the very top level of the hierarchy of SNOMED CT. And when we measure the similarity between the two terms based on path-based similarity measure, which is defined as the reciprocal of shortest path between two concepts, it is 1/12, which does not conform to our sense of similarity or relatedness. So to address the shortcomings of path-based measures, many information theory approaches were proposed, and most of them make use of the information content, which is defined as the inverse of log of the probability of the following concept and its descendants on ontology. So when we measure similarity between two words based on information content, we consider the information content of least common subschema of two concepts, or LCS of two concepts, and we measure semantic similarity using the information content with the IC of LCS of strong and info is 0 because the two concepts shows at the very top level of ontology, and the similarity between the two terms is 0, which also does not conform to our sense of relatedness. So when humans consider the likeness of two words from various perspectives of relations other than subsumption, and we can extract context around the words to measure relatedness. And we need to extract and understand the context to measure relatedness between two words. So gender is related to car, for example, and LG is somewhat related to car because LG manufactures part of a car called battery, But cluster chart is not really related to car, and you know those facts by your intuition or your previous experience. But to make understand those facts by machines or computers, we make use of the distributional hypothesis, which says similar words occur in a similar context. So when we read an article, NIH article or Wikipedia article about Chang, you will be highly likely to spot a word's car in the same article, and LG. Also, you are highly likely to spot a car in an article about LG, but you are less likely to spot words like a cluster card in an article about a car. So the word NLP technologies such as word embeddings is often based on co-occurrence statistics, and words are represented by a context factor. But we need a larger corpora to earn the enough cases of co-occurrence and obtain those information. So to eliminate the need for larger corpora, we can use ontology for the measurement of relatedness of two words. So when we use ontology, similarity takes into account easier relations within ontology only, whereas relatedness accounts all semantic relations such as part of or in the field of biomedicine has associated morphology. And this better correlates with human judgment. So, for example, stroke is not infar or vice versa, but stroke is connected to infar by the relation that has associated with morphology. And we can say that stroke is related to infar. And here I'm using a proposal of relating these measures using multiple relations to address the limitation of information content that is exclusively dependent on easy relations. So they introduced a new metric called extended information content to employ the whole set of semantic relations. And the EI's term here is the information content derived from easy hierarchy, and EIC term here is the information content derived from other attributes. And the correlation with human similarity judgment benchmark of SLA3 biomedical term pair was 0.74 when mesh was adopted as a working ontology. And they found that it better correlates with human similarity judgment than relying exclusively on easy relation. Here we propose a new vector-based model that exploits multiple semantic relations within ontology, and unlike the previous, unlike the pure and useless approach, we do not leverage information content of concepts where we derive vectors from external sources. And in this study, we adopted SNOMED CT to represent easy relation because SNOMED CT is the most comprehensive and granular biomedical ontology. And we adopted the UMLS to represent attribute relations because UMLS provides even more attribute relations than SNOMED CT. So for example, the SNOMED CT concept cerebrovascular accident has two distinct attributes and three attribute value relations on SNOMED CT, but UMLS provides 7 distinct attributes and over 200 attribute value pairs for the same defining concept. So for the illustration of the current approach, let's assume that we are measuring relatedness between stroke and infarction using the current methods, and assume that we each defining concept has one easy relation and 2 attribute relations. So the value concepts for stroke are cerebrovascular accident, epilepsy due to motor stroke, and specificity as a sequelae of stroke, which corresponds to easy concept and of course before relations respectively. And refers towards the value vector for each value concept, and the dimension of each value vector is the union of all supertypes of all value concepts. And the value vector is calculated with the rate, which is defined as the depth of the variable concept divided by the depth of value concept. So in the example of the value vector lacuna, in fact, the weight of Lachlan with respect to SNOMED CT concept is 1/8 because the depth of dimensional concept, SNOMED CT root concept is 1, and depth of Lachlan involved SNOMED CT is 8. But we further multiply rate constant K, which is 1 for easy relation, and which is set between 0 and 1 for other relations. So in the case of lacuna infra, which corresponds to non-easy relation, we multiply K that is set between 1 and 0, and we arbitrarily set K at 0.8 in this case. And the rate for lacuna infra with respect to increased also to season disorder or myocardial erosion are 0 because lacuna infra is not subsumed by those concepts. And we build we build value vectors for all value concepts. And the final context vector for the final concept in function is the average of all 3 value concepts. And we build a context vector for defining concept strong in the same way. And the relatedness between the two concepts is the cosine similarity, and is calculated as shown here. So what is running behind the scene is that when stroke and infra two vectors are represented vector space using easy relation only, the angles are quite wide because the two conception is at the very level of approach is SNOMED CT, but when we make use of other attribute relations, the cosine angle gets closer because the value concepts of each defining concept is at a lower level of hierarchy. So for the evaluation of the current approach, we employed 2 benchmark sets. The first benchmark set was built by Patterson et al. And was originally composed of composites of 30 biomedical components and 59 unique rules. And the relatedness between 2 terms were rated by physicians and coders on a scale of 1 to 4. 1 being unrelated and 4 being synonymous. But among 59 unique words, there were 2 words that lacked exact string matches for any SNOMED CT terms. So 3 pairs which contained those 2 terms was abandoned for the final evaluation. And the second benchmark set was built by Eunsuk, and it was originally contained 36 pairs. And so the relatedness of pairs were manually evaluated by medical experts on a scale of 0 to 1, 0 being unrelated and 1 being synonymous. But one pair which contained 1 term that lacked exact string matches for any SNOMED CT term was abandoned. So the final analysis, a total of 27 biomedical companies from Patterson's benchmark set, and those 35 compares from this benchmarks that were used. This result shows the number of attribute relations to each term in the Patterson's benchmark set. As you can see here, terms like HERP has over 2,000 attribute relations on the UMLS, whereas terms like stenosis has only 1 attribute relations defined on the UMLS. And this shows the number of attribute relations to each term in Eunsuk's benchmark set. And we used Spearman correlation coefficients to evaluate the performance of our approach. And on the Patterson's benchmark, the Spearman coefficient with physician and coder was 0.655 and 0.744 respectively, when K was set at 0.5. And we also measured the performance of our approach by eliminating the contribution of attribute relations. That is to say, when K was set at 0. In that case, the Spearman coefficient dropped to 0.56 and 0.558 for physicians and coders respectively. And we compared the performance of our approach to other similarity or related measures. And the path-based measures by Wu and Palmer, ice-based measures by Chang and Condas, and multiple relations by Peter and Usman, which was introduced before, the performance of those metrics were compared to our approaches and got a lower correlation coefficient than our methods. But the cutting edge word embedding methods by Park et al., which made use of Wikipedia as a external textual resource and used words to vectors to represent words, had some better correlate better correlated with pigeon encoders than our approaches. And this result shows the correlation with Korea practice benchmark. The coefficient was 0.74 when K was set at 1. And when we eliminate the contribution of attribute relations, the coefficient was 0.717 and was better correlated with the Korea practice benchmark than other similarity related measures. So one of the interesting findings of note is that we can control, or we can determine how much we will mimic the sense of relatedness perceived by coders or physicians by controlling the rate constant K. So when K is getting closer to 1, it better correlates with the doctor's ratings of relatedness, while when the K is getting closer to 0, it better correlates with the sense of relatedness perceived by coders. So we can mimic doctor's sense of relatedness by increasing K, and we can mimic the coder's sense of relatedness by decreasing K. And this implies that doctors can control of attribute relations when they consider the relatedness between two biomedical terms. And then why does ice-based matrix not work with SNOMED CT? As you have seen in the previous slides, the information content is defined as the log, inverse of the log of probability of occurring concept and in its descendants in oncology. For example, when we measure the information content of cutaneous lymphoma, for example, and eosinophilic gastritis, medical experts may consider the information content of two diseases are similar because each disease has its own pathophysiology or epidemiology or treatment modality. But in SNOMED CT, cutaneous lymphoma has more descendants and is located higher in the hierarchy. So the information content of cutaneous lymphoma is smaller than eosinophilic gastritis. And so this gap in the information content perceived by medical experts and designed by the UMLS oncology designers have led to a lower performance of ice-based metrics. And why does the relatedness matrix that use multiple relations not work with the UMLS? As we have seen before, Peer and Userness in Peer and Userness metric, the EIC here is highly dependent on the number of semantic relations assigned to a term. So the EIC of terms like hurt may be overestimated because it has more than 2,000 semantic relations assigned to the term hurt, while EIC of terms like stenosis may be underestimated because the stenosis has only one attribute relations. So the strength of the current approach is that we can overcome the inconsistencies in oncology design, and we can address design inconsistencies in the number of self-type concepts or number of attribute relations. And this is because it measures closeness of vectors by cosine similarity and not by magnitude. And the secondary use case of the current approach may be the validation and auditing of attribute relations So if we measure the relatedness between two biomedical terms using the current approach, and if you find that the relatedness score is lower than expected, we will assume that there will be totally missing attribute relations. So, for example, the relatedness score between delusion and schizophrenia in the person's benchmark study was 0.038 when measuring relatedness using the current approach. And this is lower, relatedness score lower than our expectation. In case we can add relations like associated finding between the two terms, and this will improve a relatedness score, and this will enrich the network of the UMLS. So to conclude, the addition of attribute relations better confirms to human sense of relatedness, and the performance of our approach were comparable to cutting edge or the embedding methods. And we can control how much attribute relations contribute to the relatedness measure by controlling a rate constant. And there was no need for larger version cohort to obtain context information, and which use existing resources called ontologies to secure the reusability of knowledge. And it is unlike information content-based approaches that are vulnerable to design inconsistencies. Our approach is robust to design inconsistencies of ontologies because and this is the merit of the vector representation of context information. Thank you for listening, and I appreciate your suggestions or questions.
Thank you, Eunsuk. Will I take any questions from here and anyone online if you want to use your function? Anyone got any questions? That was quite an amazing, detailed presentation. I followed some of it. I'll not pretend I followed all. It was pretty good. But any questions, Patrick?
So with the UMLS, there were 200 vocabularies in there. Did you use the full set?
No.
English only, but did you subset
No.
sources?
No, there was some attributions that represent some historic data, or that does not represent any meaningful relations between terms. So I eliminated some attributions that is related to not to be much related to the current version of the UMLS or historic data.
So this was from sources.
Yeah.
Thank you.
Any more questions?
That was very interesting.
Thank you.
I think I followed. How is this used? What's the output? What's it applied?
So the merit of the current approach is that we do not need large corpora. So previous related measures made use of like corporas like Wikipedia, but those resources are highly biased, I think. And especially when it comes to measuring two biomedical terms that represent some rare diseases, the measurement of the matrix that uses corpora or external textual resources cannot be applied. So, for example, the progressive multifocal glucose encephalopathy is the rare complication of AIDS. But when you take a look at the Wikipedia article about AIDS, you cannot spot words progressive multifocal glucose encephalopathy. So you cannot measure relatedness between AIDS and multifocal progressive multifocal glucose encephalopathy when the metric is based on the Wikipedia. But it is represented on SNOMED CT that PML is the complication of AIDS. So that is the merit. Merit of using SNOMED CT when it comes to rare diseases or rare cases of myelomedis. Yeah.
Was there a specific thought process that made you choose to represent that semantic relationship between the two terms?
Because SNOMED CT provides the most granular and most comprehensive semantic network among biomedical terms. So it can be used to measure relatedness between drug interactions or drug disease relations or pathophysiology disease relations. Yeah.
Questions? Yeah. Anything online? Nope, no questions online. And I think that concludes this afternoon session. Thank you, Eunsuk, and thank you for coming in and giving a talk today. Online delegates can join a few more sessions through the event lobby, and we thank you all and have a great day. Thank you.